welcome to today's webinar with the title Cost-Efficient Flexibility, Physical PCB Sample WE.bend. I am Andreas Schirp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik, Verena Krug from our Technical Project Management. Welcome back, Verena. And now I wish you lots of fun and new information.
So, thank you very much, Andreas. Also welcome from my side. As mentioned, my name is Verena Krug and I work at Würth Elektronik since 2012. And in the last 7 years I've been working in the Technical Project Management, where we do some special customer projects, especially for 3D technologies. So for example, RIGID.flex PCBs, but also SEMI.flex and BEND.flex, about which technologies we will talk today. So first of all, I will introduce you the new physical PCB sample for SEMI.flex and BEND.flex, and afterwards we will have a deeper look at those both technologies and their bending cycles and radius, and of course on the costs. We start with the physical PCB sample. Here you can see the top side. We have here different areas. The first areas that I would like to show you are the BEND.flex areas. The BEND.flex technology is based on the RIGID.flex technology, but in this case we do not use polyimide, we use only FR4. So also in the flex area we have pure FR4. We have here a special production process so that the FR4 is not damaged by the deep milling, and so it's very smooth and can be bent very well. In this case, those areas can have 2 copper layers in the bending areas, and we have the one on the left side which can be bent with 180 degree and the other one can be bent with 90 degree. The areas are bent with 3 mm bending radius. Maybe you know from SEMI.flex that the bending radius is a bit higher. You can see here our table about it, and you see BEND.flex can be bent with 3 mm for the double layered flex areas. If we have only 1 layer in the flex area, the BEND.flex can also be bent with 2 mm. That makes it possible that the bend areas are very small. So in this case, the one on the left side is only 9.4 mm, and the one on the right side is only 4.7 mm, so very small. Another good thing that we have here is a BGA with 0.8 mm pitch, which is, compared to other technologies, a big BGA. We can also do smaller BGAs, but this one has the advantage that we can use a dog bone structure, and therefore we do not need any filling process or microvias or buried vias or something else that makes the PCB a lot more expensive.
Less expensive.
Yeah, the BGA makes it less expensive, exactly. On the back side, we have the SEMI.flex areas. And again the BGA. Here in the SEMI.flex area on the left side we have 1 copper layer in the bending area, and we can bend it with 90 degree. To compare it with the BEND.flex, here we have a width of 7.1 mm for 90 degree, as you can see in the table. For the BEND.flex we have approximately 9.4 mm, and we can already bend it across 180 degree, and we have 2 layers in the flex area. So here you can already see that the BEND.flex is a lot more bendable than SEMI.flex. The second SEMI.flex area here includes 2 copper layers, and this can be bent again with 90 degree, but here the length of the flex area is 8.7 mm. So again the flex is a bit smaller than the one from the BEND.flex, but we can bend it only with 90 degree and not with 180 degree. You can also see that we have small radii at the flex rigid intersection, and those are needed to have enough stability between the semi-flex area and the rigid area. This is only needed for semi-flex, not for bend flex. The last thing that we can see here very well at the backside is the QR code. Here you can, if you scan the QR code, you will be led to our webpage where you find more information about bend flex and semi-flex. And here you can also pre-order the sample so that you can really have it in your hands and see the difference between the bending properties of semi-flex and bend flex. Of course, we can bend this sample, as you can see here. Here we have all areas bent with copper in the outer radius. For semi-flex, it's only allowed to bend it in this way. The bend flex, which is on the right side, can be bent also in the other direction, like this, so that the copper is on the inner radii for those two areas. This is a benefit that we have for the bend flex. For semi-flex, it's not possible, but with bend flex, we can do it. So why do we have this difference? The difference is created by the stack up, which we can see here. On the left side, we have the bend flex area. Here you can see that we have a core, which is dark gray, and then we have copper, and again pre-preg underneath, and again copper. This area is made based on a rigid flex process flow, and that means that the glass and resin of the FR4 is not damaged, and therefore it can be bent very well and very smooth. On the right side and in the middle, you can see the semi-flex area. The one on the right side has one layer in the bending area, and the one in the middle has two layers in the bending area. And here you can see a small face at the rigid flex intersection. This phase is created when we do the deep milling of the flex area or of the semi-flex area to make the material thinner so that it's bendable. So if we compare bend flex and semi-flex, then we have main differences between those two technologies. One big point is the material. So for semi-flex, we can use only TG135 base material, because the material with a higher TG has different filling materials in it and is more stiff. So for the semi-flex technology, it's not usable. For the bend flex, we can use it because it won't be damaged, and so the material can be bent very well. We can use for both technologies ED copper, and we add galvanic copper as usually for the outer layers, for multi-layers and rigid flex and so on. In both cases, we can use coverlay or flexible solder mask. We recommend to use flexible solder mask if it's possible, because we have to place the coverlay by hand, and so this is very cost intensive. Maybe you have seen another webinar about the costs of PCBs, and there you can definitely see that a coverlay is a big point for higher costs. As mentioned, for the semi-flex, we do a controlled deep milling in Z-axis with a 45-degree phase. The problem here is, or what means the problem, the one difference to the bend flex is that with the deep milling, we mill into the glass and the resin matrix, so it will be damaged, and therefore it's only bendable for a few times, and only in one direction, so only with the copper on the outer radius. As mentioned, bend flex will be produced in another way. We will see later how it will be produced. It's based on rigid flex production, and so the glass and the resin is not damaged. What makes it a bit smoother, we have a defined thickness in all areas of the bending area, and that makes it possible that the copper can be on the inner and on the outer radius. So let's have a look at the production process. So maybe you have seen semi-flex before. Semi-flex is produced like every multi-layer is produced. So we have the inner layer production processes where we do the etching and layouting and so on. Afterwards, everything will be pressed together with prepreg in between. Then we do the drilling and the plating to have a connection between outer layer and inner layer. Afterwards, we will do the layouting of the outer layers. We will add solder mask and flex mask in the bending area. But now the PCB is not bendable, and that's why we do a deep milling in the bend area or in the SEMI.flex area, that the material is a lot more thinner, so approximately 0.2 millimeter. And with this reduced thickness in the bend area or in the SEMI.flex area, we can bend the PCB. As mentioned, the glass and the resin will be damaged. That's why we have to have a look at the used prepreg, because it has a big impact. You can see here our prepreg types that are usually used at the market. On the left side we have the thinnest prepreg, the 106, which has a thickness of 50 to 55 microns. And on the right side you see the thickest prepreg with 170 to 190 micron. So normally for SEMI.flex we use the two prepregs in the middle, so the 1080 and the 2116. Both have a thickness around 60 to 100 microns. You can see on the pictures that the glass is not that thick, so it's a bit more bendable. And if we do a SEMI.flex with those glasses or with those prepregs, then it looks like this. So we have a very smooth SEMI.flex area. You cannot see a lot of white areas where the glass is really damaged. But if we use, on the other hand, the 7628, then the bending area will look like this. You can see all the white areas, and here we have massively damaged the glass. So when we bend this PCB, it will definitely break. Where is this technology used? I have one example for you. Here we have a switch box for soil analysis. Some people use it to see what is underneath our ground, so in several meters deep. They use, therefore, the resistance and the induced polarization image that they can see with this machine. Here in this area, or here in this case, you see on the right side the PCB. It has 156 relays on it. The biggest advantage that we here have is to save some space, because you can see in the middle, on the picture in the middle, that the PCB will be bent like a S or like a W, and so we save a lot of space. The bended PCB will be mounted on a metal plate, and then it will be implemented in the final product. Yeah, as mentioned, the advantages are the miniaturization, because they can use 4 times the signals that they use in the housing before with this technology. Then, of course, the costs are less expensive, because we do not need cables and conductors. And we have a higher reliability, because we have only one design. We have one assembling, one soldering, one testing. We have less soldering areas that might break, and we have less material in it, so less cables and connectors which have potentially problems or failures. On the other hand, we have the BEND.flex process. So BEND.flex looks very similar to a 1F-XRI stack-up, but you can see between layer 1 and layer 2 there is a dark gray part which goes through the bending area. For a 1F-XRI, for RIGID.flex, this is normally the polyimide. In this case, we have here a normal FR4. In this case, especially a core, a very thin core, which will not be damaged by deep milling or something like that. We do it like a RIGID.flex 1F and use FR4 instead of a polyimide, and so it will not be damaged. One very cool application that we have done is here this pneumatic system for our customer Festo. Festo came to us with different requirements. They wanted a good signal transfer, which is definitely done by RIGID.flex technologies or by BEND.flex technologies, because here we do not have to use a connector and a cable between the PCBs. That means the signal can run over the PCB and does not have to go through a connector, a cable, a connector, and then again through the PCB. So it's a lot more stable. Another big requirement of Festo was the mechanical stability for the installation. We will see on the next slide how it will be installed. They had low space, so that's why they did not want to have a wiring solution. Moreover, for the miniaturization, it was important to have microvias over 3 layers, which is not a standard. Also important was the vibration resistance, which is not given by SEMI.flex, for example. They wanted low testing costs, low procurement costs, and low logistic costs. And all this can be done with one technology, and this is the bend.flex technology. You can see here how the PCB looks like in the picture on the right side. We have here a dark part, a black part, where the PCB will be pushed through, and then the edges will be put down and clipped into the housing. The goal was to have a fully automated assembly, and now Festo has a fully automated assembly. When they started with the first samples, it was bent by hand, so that's why they wanted enough stability to get it through the housing, but also enough bendability to bend it by hand. The big advantages here have been the miniaturization, because we have no cables, no connectors, and we have microvias from layer 1 to layer 3. The reliability is a lot more higher because we have less solder areas and only one system. And of course we have a system advantage, because the customer can can install the PCB fully automated. So if we have a look at the Stackup, then you can see here how it's produced. We have between layer 1 and layer 2 a prepreg, which has only 65 microns. Underneath we have base copper, 70 microns, and then a very thin core. And you can see that we have here the microvias from layer 1 to layer 2. Layer 1 to layer 2, and from layer 1 to layer 3. Due to the thin prepreg and the thin core and the thin base copper, we can use here normal microvias with 150 microns diameter and pads with 350 microns. So this is also a good opportunity to use for the bend.flex. So now let's compare the bending cycles and the costs. I have here a diagram for you where you can see on the left side a multilayer. The multilayer is our base with 100% of the costs and no bending, so that it cannot be bent. The next one is the SEMI.flex, where you can see we have 125% of the cost, so there's an increase of 25%, but the SEMI.flex can already be bent 10 times. The next part is the bend.flex with 170% of the costs and 20 bending cycles. And you can see here that the bend.flex is a very cost-efficient solution, because if we use, for example, a RIGID.flex with 2 layers in the flex area, then we have 280% of the costs and 100 time bending. But normally, most of the customers do not need 100 time bending. They need only 10 to 20 times, because you have the installation. Maybe you have to put it out again and then have a look or something like that and put it in again. So approximately 10 to 20 bending cycles would be good. And for the bend.flex, you have exactly those 20 bending cycles, but only 170% of the costs instead of 280 for a 2FXRI. Moreover, we have a very small bending radius. So if we keep our example, then we have a flex area with 2 layers, which we can bend with 2 mm bending radius. But you see that the bend flex with 2 layers can be bent with 3 mm bending radius, which is also very good. So even here, the bend flex and the semi-flex, of course, as well, is more cost efficient than a rigid flex. So if we come to a conclusion, then we can see that both technologies are less expensive than rigid flex. And here we have 2 main factors. The first one is that the polyimide is not used, which is a lot more expensive than FR4. And the second one is that both technologies do not have to be dried before soldering. So you can, you don't need a special process for it and a good plan to solder it after drying in 24 hours. It's just not necessary. What is very important for those technologies is that you talk to us about the Stackups. So if you have a concrete case where you want to use semi-flex or bend flex, please let us know at flex@we-online.com. We can have a look and we can help you with the Stackups so that the PCB can be bent very good afterwards. You have seen that a bend flex can be bent more frequently. If you order the samples, you can directly see how good bend flex can be bent compared to semi-flex in both directions. So please feel free to order it. Bend flex can also be bent with smaller bending radius, which is nearly as small as the bending radius for rigid flex, but as mentioned before, it's more cost efficient. The combination with HDI is possible, so microvias from layer 1 to layer 3, which is not common. And if you want to have all those important informations and do a pre-ordering of the samples, you can click at this link, or you can scan the QR code from the beginning. Here you can do the pre-order and see everything that's necessary.